Hi, I'm gonna teach section 1.6 today. It's more on functions. Okay, here I hope to discuss these topics using zeros. Um, Thereby, I supposed to discuss zeros, introduce zeros, what are they, how to use that, etc. Um, then I'm gonna discuss symmetry, symmetry about y-axis, which is called even functions, and symmetry about the origin, which is called odd functions, um, and rational functions. A little bit. We're going to discuss more in section 2, right? Uh, okay. Zeros. What are zeros? Um, Zeros are, in simple, zeros are x-intercepts, right? Where the function crosses x-axis. Okay. For instance, now if you have x and y axis like this, say you have a function like this, x-axis and y-axis. At these 2 points, this function fx intersect the x-axis. Fx intersect the x-axis at these 2 points. So these are x-intercepts, or we call x-intercepts. Same thing we call as zeros. This point and this point as well, right? Um, so from this point onwards, uh, wherever function intersect x-axis, in other words, x-intercepts, I call them zeros. Okay. All right. Now you know what are zeros. Let's do this example 1. Find zeros of the quadratic function defined by equation fx equals x squared minus 5x plus 6. This one. We know this. Okay. We're gonna um, find zeros of this. Um, we already know this shape. Um, this x squared minus 5x plus 6. We discussed this type of functions in previous section 1.5 under parabola. This is a quadratic uh, function. We know it is a parabola, but for the time being, let's assume we don't know that, right? Let's assume we don't know it is a parabola. We want to find the zeros, its x-intercepts. Uh, we already know how to find it. So in the same way, we're going to find it. For x-intercept, we set fx to 0. For x-intercept, we set fx to 0. Now we call it zeros here. For zeros, we set fx equal to 0. That means right side is 0. Then we factor this. We get these factors, x minus 3, x minus 2 equal to 0. Then by using zero product rule, we can say we can set each factor to 0. X minus 3 equal to 0 and x minus 2 equal to 0. Each factor to 0. Um, then solving those two linear equations, we get x equal to 3 and x equal to 2. So far, nothing new. Right? The only thing new was this term zeros. Beside this term zeros, um, everything else uh, are you familiar with. Let me clear this. Okay. Now, sign analysis. This is also not something new. Uh, we learned this in section 0.5. Um, I also did a video on this. I told you, uh, I think almost everybody watched that. So I believe you familiar with this sign analysis. Um, let's do this sign analysis on this function fx, right? Um, we know uh, in above example fx equal this has two zeros. We get two zeros x equal to 3 and x equal to 2. These are the two zeros. Now we want to find out what happened to the function before those zeros and after those zeros. Right? Clear? Um, we want to find out what's happening to this function before means outside these x values, right? When x equal to 3 and x equal to 2, its y coordinate is 0. We want to find out um, at other x values what's going to happen to this function, right? If it is increasing, decreasing, or means if it is basically we want to find out if it is on positive side, means above the x-axis or below the x-axis, right? From sign analysis, that's exactly what we expect to find. Um, now we want to find what's happening to the um, function before those zeros and after those zeros. Uh, for that, we use the sign analysis. This is how we do it. Uh, this is discussed again in that video. Also, we learned this before, but I'm doing it again. Now, this is the given function fx equals x minus 3, x minus 2. We already found it has two zeros. So these x values, I wrote it under this horizontal line. This horizontal line, assume it is x-axis. So at 2, we have 2 and 3. So it is obvious 2 should come left side of 3, because 2 is smaller than 3. This is x-axis, like number line, right? Now we want to, okay, on above the x-axis, you see these zeros, that means the y value. Y value, I put uh, here on this line, this 0 at x equal to 2, and again y value is 0 at x equal to 3. Now left to x equals 2, left to x equals 2 means in this region, let's see what's the sign. That means, as I said, in sign analysis, what we expect to do or what we expect to find is uh, if the function is above the x-axis or below the x-axis. That's exactly what we want to find, right? Now, to find that, what we do is we get a check number, check value, left to x equal to. Here I use these check values in this example. So let's do 2, I use 1. You can use 0, nothing wrong. Now if you use 1 here, I show you the first one means in this region, we get in first parenthesis 1 minus 3 and 1 minus 2. 1 minus 3 is negative number, is negative 2, 1 minus, we just want the sign, don't worry about the number. 1 minus 2 is negative 1, again, we just need the sign, negative and negative. So these two negatives give this positive. Negative times negative is positive. That's how I get this positive. Positive means we get y value positive. That means it is above the x-axis, right? Above the x-axis, y value is positive. Since we get plus here, we know the function is above the x-axis. In the same way, if you substitute number in between 2 and 3, if you substitute a number in between 2 and 3, here I pick 2.5. Now, you don't have to show this thing 1 minus 3, I mean this step. These things you don't have to show, but if you want, write it down without making mistakes. Write the second one also. Now what we substitute in 2.5. When it is 2.5, it is less than 3. Therefore, first parenthesis is negative. Second parenthesis, x is 2.5 minus 2, it is positive. Positive and negative gives us negative. That is what I put here, right? In that way, if you substitute a number greater than 3, 3 minus greater than 3, that means we have to substitute a number greater than 3, which is 4, 5, any number greater than 3. So I pick number 4. 4 minus 3, it is positive. In this region, first parenthesis, positive. 4 minus 3, 4 minus 2, again it is positive. So we get plus here, right? That means when x is less than 2, function is above x-axis. In between 2 and 3, function is below x-axis because it is negative. Again, after x equals 3, uh, function is positive above the x-axis, right? So I wrote the sign analysis result here, what happened in each region, and I uh, I did the graph using that sign analysis result. Below 2, the graph is f is positive. Between 2 and 3, graph is negative. After 3, the graph is positive. Now, you see, I did the parabola with this sign analysis result and using zeros, which so far we learned in this lesson. I ask you to assume we don't know if this quadratic function is a parabola. This graph, we don't know it is parabola. The only thing we know, if we use what we learned in this lesson so far, we know before 2 the graph is positive. After 2 it is negative. Between 2 and 3 Again, shape we don't know. Um, I mean, you should not uh, break rules of function. See here, I break the rules of function. Um, Without breaking rules means you cannot have 2 points on the same vertical line. Um, it can go up and down um, from here, go like this. It like this, right? There are many ways, thousands of ways. The only thing uh, before x equal to f should be, this is f. The function should be above x-axis. Between 2 and 3, it is below x-axis. After 3, it is again above x-axis. Right. This idea can be extended to higher order polynomial functions, provided we can determine all zeros. If it is factorable, it is easy. Um, okay. Once the zeros are located using sign analysis, we can draw graphical representation. This is really not the graph. It is a rough sketch or graphical representation of the function, what we do here, right? So with what we learned so far, uh, we don't know a lot about this function. Means, look, this shape, this shape here. Okay, let's see. These shapes here, we don't know. These things undetermined. Right? Um, we want to find a way to uh, figure out the exact shape. Um, we will see that once we do calculus, once we get into calculus in section 2. All right, let's move on. As I said here, I discussed, we still don't know a lot about this, where it is increasing, decreasing, basically the shape of the function. Uh, when I say shape, that means, okay, we know it is coming to this point, but if we don't know if it comes like this, or even here, we don't know if it goes like this, or if it goes like this, right? It could be this red line, it could be this black line, or none of these two, right? So this red shape, it is concaving up. This black shape, black line is concave down. We're gonna discuss that these things under calculus. Um, so for the time being, what I want to tell you is concavity of the graph, we don't know it, right? Means the shape. Okay. Sketch the graph of this function x cubed minus 9x. Okay, what we got to do is the thing that we are very familiar with. We want to find zeros. For that, we For that, we factor this function, uh, take x out, we get x square minus 9, and this is difference between two perfect squares. By factoring again, we get x minus 3 and x plus 3, setting each factor to 0, um, and solving these linear equations. I'm just going through this because you guys know very well how to find these zeros. We learned the same thing with a different name, x-intercept. So we get these answers, x equals 0, 3, and negative 3. Setting these individual factors to 0, we get these three answers. Now, here also, this is the x-axis. Below x-axis, I showed you x values. Here, I showed you y values at when x is negative 3, 0, and 3. We get corresponding y value 0. It's all zeros, right? Negative 3, 0, and 3. All y values are zeros. We want to find out the sign of the function, if the function is above the x-axis or below the axis. If we get plus positive answer, function is above x-axis. If we get negative answer, function is below x-axis. Now, to determine that, I use these check values. I showed in red those check values. Less than negative 3, I use negative 4. Between negative 3 and 0, I got negative 2, 0 and 3, I use 1. More than 3, I use 4. When I substitute these numbers, these check numbers, negative 4, etc., etc., when you substitute in the factored form of the function, right? Okay, I wrote it for the convenient here. So if you substitute negative 4, this is negative, then negative 4 minus 3, again it is negative, negative 4 plus 3 is also negative. Three negatives, when you multiply, you get this negative sign here. Likewise, we get positive in this region, negative in this region, and positive in this region, right? Okay, now we can do the graph according to the sign analysis we did. Um, Before x equal to negative 3, function is minus. Therefore, before negative 3, the function is in negative region. The thing is, we don't know the exact shape. It could be like this, right? Between negative 3 and 0, it is positive. It is negative 3 and 0 in this region. Again, we don't know this shape. We don't even know it turn around at this point, right? The maximum here, we don't know. It could be something like this, who knows, right? Uh, between 0 and 3, it is below the x-axis. After that, it is above the x-axis. Story is the same. It could be any shape, right? Okay, let's move on. Example 3, right? Sketch the graph of this function, x to the 4 plus 4x squared plus 4. Now here I'm going to discuss these properties. Let's get the marker. I'm going to discuss these properties of this graph. We have, this is what given, right? We know the first step, we have to factor this out. We learned how to factor. I'm not going to discuss factoring here. If you have any questions, let me know. This is x squared plus 2 times x squared plus 2, or you can say x squared plus 2 whole thing square. Right? Okay, now just to let you know, we can write this as quadratic equation of x squared. X squared to the 2 is x to the 4 plus 4 x squared to the 1 plus 4. Now if you substitute x squared equal u, then you get u squared plus 4u plus 4. You can factor this out. This is u plus 2 whole thing square. Resubstitute u equals x squared. You get x squared plus 2 whole thing square. Right? Now, this is a quadratic function of x squared, but it is not quadratic function of x. It is x to the power 4. It is fourth degree polynomial function. So it is not a parabola. We learned quadratic functions are parabolas, but this is a quaternary function. That means x to the power 4, fourth degree polynomial. It is not a parabola, but since it is a quadratic function of x square, it looks like a parabola, but it is not a parabola or parabolic shape. Okay, I got to erase this thing to move on. Okay, we found factors. Let's see if I can get the marker. No, that's bad. Let me use this one. Okay. I use this marker. Hopefully it move with the slide. X square plus 2 whole thing square. Yeah, moving. Okay, now if we do the graph of this, uh, we get this shape, but uh, I didn't discuss it. We have to find zeros. For that, we set this to 0. If you set this to 0, this means if you get the square root on both sides, we get x square plus 2 equal to 0. Square root is 0. We get x square equal to negative 2. Then x equal to plus minus square root of negative 2, which is not real. This is not real. Right? What that means? X has no real solutions. That means uh, this graph never intersect the x-axis, right? Means there are no zeros. What this means? This implies fx has no zeros. Also, we saw when we factor this, it was x square plus 2 to the power 2. For any x value, you cannot make this function negative. If you substitute any x value, any negative value, positive value, 0, whatever it is, it gives you a positive number. Such functions are called positive functions. Right? So we can expect this function is always above the x-axis. It never intersects x-axis. Since I said it looks like a parabola, but it is not really a parabola, I did do a parabolic shape here, you see here. But if we do the graph with what we really know at the moment, we cannot do a parabola. We can assume we have a minimum value here because when x equals 0, this graph, this equation, uh, this reports the lowest value. Therefore, we can assume there is a minimum value, but beside that, we don't know the rest of the graph, how it's behaving, right? Or next at my coordinate system. Okay. Um, now we move on to um, symmetry, finding symmetry. Um, let's first discuss the even functions. Even functions, which means symmetry about y-axis. How we check if the function is even? We find f of negative x, means we replace x with negative x. When we do it, if we get the same function fx, then we say f is an even function. Okay. For polynomial functions have y-axis symmetry, x must appear only to even powers, and that is the reason they call even functions. Means when you write the equation, in the x must appear only to even powers. right? Not on powers. Then we can say, okay, just looking at the equation of the function, we can say it is a even function, means it is symmetric about y-axis. This thing is good to know. Um, the mirror image of xy on y-axis is negative x, negative y, right? Now, the importance of this symmetries is if we could find if the function is even, then we have to worry about only one half of the graph. If you know this half is like this, then you can complete the other half uh, just looking at this half and making the mirror image on y-axis like this dotted line. Right? Okay, I'm gonna do that example. Um, so non-polynomial functions can also exhibit even symmetry. I give two examples: the absolute value or fx equals x to the power 2 over 3, means with this rational exponent 2 over 3, but still look, its power is even. The radical part is odd, but power is even. Um, continuous function, continuous means the graph has no holes or jumps, must have turning point at its y-intercept. Those continuous functions, they must have their turning points at its y-intercept. We're gonna see why it happens, right? Let's do this example for sketch the graph of y fx equals x squared. Um, First, let's check the symmetry. For symmetry, we find f of negative x. We won't find this. How we find it? Substitute negative x on the right side of the equation. So for x, we substitute negative x square again equal to x square, which is same as the right side of the equation. Therefore, it is equal to fx. That means f of negative x. When we find f of negative x, we get same fx, right? That means the function is even. Therefore, it is symmetric about y-axis. Okay. Um, we drew this graph under parabola. How we did that? Um, I told you, since it is not a straight line, we have to find at least 5, 6, 7, 8 points. Um, so for that, we select um, x values, uh, x values, and then found corresponding y values, substituting that on the right side of the equation. Then we did the graph. But now, since we know this graph has y-axis symmetry, since it is an even function, we can find only one side of the uh, y-axis. Means here I found only the right side of the y-axis values. Then we can create the left side of the y-axis using symmetry, right? So when I got just three values, 0, 1, 2. When you square these values, we get 0, 1, 4. Using that, I did this, the left side of the graph, this side of the graph. Then looking at um, this, and getting the mirror image on y-axis. That means assuming this y-axis is a mirror, I do the mirror image, that is this red line. Red line is the mirror image of blue line. See, here in the table, I do not find any x negative value. Negative x values I did not find here. I did the negative part just using the symmetry. Okay, let's move on. Okay. Show the function whose equation x equals x to the 4 minus 3x squared plus 12 is even. How we show it is even? We won't find f of negative x. When we find f of negative x, if we get the same answer as the given expression, we can say it is an even function. If not, we cannot say it is an even function. Substitute x equals negative x to the 4 minus 3 times negative x square plus 12. Then negative number to the power 4 is again a positive number. X to the power 4. Negative number to the even power is a positive number. That means negative number to the power even power is a positive number. This is positive. This positive and this negative. This is positive and this negative gives us negative 3x square plus 12, right? X to the power 4 minus 3x square plus 12. Now, if you compare that with the original equation for fx, you see these two expressions are the same, the right side expressions. Therefore, we can say this is equal to f of x. Means what we get finally, f of negative x, we found it is equal to f of x. Therefore, we can say, therefore, fx is an even function. Okay, it is an even function. Okay, example 6. Show the graph of the equation y cubed minus 3x squared y minus 23 equal to 0 is symmetric about y-axis. Symmetric about y-axis. How we show it is symmetric about y-axis? To show this, show this is even. Right? That's it. How we show it is even, replace x with negative x. Replace x with negative x. So this is the given equation. Here I'm gonna replace x with negative x. (23). Now let's simplify this. Y cube minus, now here again negative x square is positive x square, therefore this is negative 3x square y minus 23 equal to 0. See this again, we get the same equation as given originally. Therefore, we can say Therefore, the given graph is even. Okay, all right. That's about even functions. Now, odd functions. What are odd functions? Odd functions means if the function has symmetry about the origin. Now, when we discuss about y-axis symmetry, we assume y-axis is a mirror. To get the uh, origin symmetry, each point on the right side of the graph, uh, I'll give you a simple example. So it has to go through um, wait, let me cross this out. It has to go through the origin. So each point on the positive side, x, y, each point is translated through the origin and you get the corresponding point on the other side. Means it is just like you translating through the origin, like uh, assume you have a point mirror at the origin. It is just like that. Each point on the right side, if you translate through this mirror, point mirror at the origin, we can create the left side of the graph, right? How we check if the given function has such symmetry? Again, we find f of negative x. Same thing that we found for even functions. Um, for even functions, when we calculate this, we got the same function. But here, with odd functions, we should get the negative of the given function. If f of negative x equal to negative fx, then f is an odd function. The reflection of point x comma y about the origin, this is good to know, it is negative x, negative y. You have to change sign of both coordinates x and y to negative x, negative y. Okay, graphs of continuous odd functions pass through the origin. I showed it on the here. It has to pass through the origin. Um, the shape, concavity of the um, curve changes at the point as well. So see, uh, before, I mean, on the right side of the x-axis, it is concaving up. Left side of the x-axis, it is concave down, right? So concavity changes here. We still not discuss the concavity. Do not worry about it. We're gonna discuss that in section 2. Okay, okay. But for the time being, let's discuss a couple of examples uh, for odd functions. Show the function defined by the equation fx equals uh, this fx equals 4x cubed minus 2x is an odd function. What we do, we find the same f of negative x. That means replace x with negative x in the given equation. So in place of x, I put negative x here, negative x cubed minus 2 times negative x. Negative x cubed is negative. That negative and this positive is negative 4x cubed. Again, negative 2 times negative x is positive 2x. Right? Now, from these two, if you take a negative sign out, You may assume you take in negative 1 out, you get 4x cubed minus 2x. Means if you distribute negative times positive, you get this negative times negative, again this positive. You can distribute this and check back. You get a negative sign out, we get 4x cubed minus 2x. Now what is this 4x cubed minus 2x, this part? It is the given function, fx, beside this negative in front. Therefore, we can write this as negative f of x. So we 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 were calculating what f of negative x. We came up with this. We obtained negative f of x. Therefore, we can say fx is an odd function. Now, let's see example 8. Xy minus 2x to the power 5 y cube equal to 0 is symmetric with respect to the origin symmetry. Once we see uh, origin symmetry, that means we have to show it is an odd function. Show the function is odd. Uh, Now, to show function is odd, now before we substitute x equals negative x, but look here, variables are uh, inseparable. Means you cannot separate x and y variables here, right? Or it is very hard to separate them, right? In either case, what we can do is we can replace x with negative x and y with negative y, and y with negative y. Means we replace both. We substitute for both x and y. X negative x for x and negative y for y. When we substitute that in the given equation, x y becomes negative x negative y minus 2 times negative x to the power 5 y to the cube is negative y to the power 3 equal to 0. Negative x negative y is xy, negative x to the power 5 odd power. This is negative. Negative y to the third power. Again, it is odd. Still, we get a negative number here. So we got to multiply negative 2 times times negative. That means we multiply 3 negatives on the row. So we should get negative answer. That's how we get this negative. Minus 2x to the 5 y cube equal to 0. Now, you see, when we substitute for both, when we replace x and y with negative x and negative y, we should get the same answer. Let's check. This is the given equation. I wrote it here, this one, and when we replace it, this is the one we get. They are the same. What that means? Therefore, we can say, therefore, the given equation is odd. Okay, that means it has origin symmetry. Origin symmetry. All right. Okay. Rational functions. Um, Functions defined by an equation of the form Rx equal to nx over dx. Means the function defined as a ratio of two polynomials, nx and dx are two polynomials. Um, then this Rx is called a rational function. Right? We're going to discuss uh, rational functions in more detail under section 2. Right? Um, for the time being, what we're going to do is just discuss the symmetry of this. Um, discuss the symmetry of the rational function defined by the equation Rx equals x divided by x to the 4 minus 4. Right. For either case, we have to find r of negative x, means substitute x with negative x. So we get negative x. I'm substituting x with negative x divided by x square. We get negative x square minus 4. What we get? Negative x divided by negative x whole thing square is positive x square minus 4. Now, can we write this as um, negative? Now look, this thing. This part is what? That is the that is same as the given um, equation, the right side, right? Therefore, we can say this is Rx. This is equal to negative of R of x. Therefore, what we get finally when we going to find R of negative x, we found it is same as negative Rx. Therefore, Rx has origin symmetry. Okay. Now, here we don't sketch the graph, but it is good to know what type of graph we get here. This function is 0. When the numerator is 0, we're going to discuss this back again in section 2. When numerator is 0, x is 0, therefore we can assume it is crossing the x-axis at the origin. Let me share this. I did the graph. I'm going to share that. Okay, let me get this graph. It's divided by x square minus 4. Okay. I got this graph. See, I doubt if I can write here. No, I cannot write there. You see, it is crossing at the origin. Again, the symmetry. That's the thing I want to show you. This point, when I'm moving, see, I'm trying to get the where it's crossing sharp y equals 2 line. So we get closely it is negative 1.76. So how we get the uh, corresponding symmetry point on the other side, we have to change sign of both. So that translates through the origin to this point. You see x coordinate is positive, y coordinate is negative. If I go back to this point, x coordinate is negative, y is positive, corresponding point, translated point here, x coordinate is positive, while y coordinate is negative. Same thing with this half, the right side thing, it translates into this left side thing, which is going down. Um, so this is the origin symmetry. The graph I showed you before, which I said looks like a parabola, but not a parabola. This is the real shape. It's crossing the y-axis at 4, right? Uh, okay, that's not what we've been discussing, the origin symmetry one. So this is the, here, it's a nice example to see the origin symmetry. All right, let's go get back to the lecture note. Okay, that's all about what we're going to discuss under rational functions here in section 1.6. We will learn more in section 2. All right. Okay, this is all what I have for section 1.6. Thank you for watching this. Bye.